So for the PID controller with multiple set point, after we run the Simulink, this is the graph that we will get for the PID controller. So for comparison and discussion, by comparing the performance result from the servo control with single set point and regulatory control with single lot, the overall figure of merits is reduced significantly when multiple set points and disturbance are implemented in servo and regulatory control. Hence, the overshoot and the oscillation of the response curve is found decreased too when multiple set point and disturbance are implemented, and hence faster settling time is achieved. In short, implementing multiple set point and disturbance will help to increase the performance output of the control system. Last but not least, PID controllers still show the greatest performance when multiple set points and disturbance are implemented. So, the next question is, tune your controller with two tuning methods of the following and compare the result. A. The Ziegler-Nichols, and B. The Cohen-Kuhn method. For the Ziegler-Nichols method, the PID controller in Simulink was set to peak mode control. Thus, only the value Kc is being changed to a value where the system starts to exhibit oscillatory response. When the value of Kc starts to exhibit constant oscillatory response in the output, the critical value Kc is marked as the ultimate gain. Ku and the period of the oscillation Pu is referred as the ultimate period. By using the values of ultimate gain, Ku and period Pu, the integral time constant and derivative time constant are determined by using the following Ziegler-Nichols controller setting for proportional P, proportional integral Pi, and proportional integral derivative PID control. It is concluded that for this system, PID controller gives a better response compared to P and PI controller. Thus, the PID controller is selected for tuning. This is the block diagram for Ziegler-Nichols. So you from the Simulink. This is the Nichols diagram. To get this frequency response for Ziegler-Nichols, I'll set the case the AU, 1 over TAUI and TAUD is set to 0. And once I run the simulation, I'll get this graph here. From this graph here, then I can determine the other parameters for the PID controller such as the GC, KC, TI, tau I, and tau D. So for the KC, I got 1360.2, while for tau I got 2.656, and for tau D, I got 0.664. Since all the parameters have been determined, now we can determine the shape of graph PID for Ziegler-Nichols. Once I run this, I'll get this graph. I can't run it now because it usually will take time and it causes lag for this video. But I have put all the input for the KC, T over TAUI, and TAUD. This is the for tuning PID in Ziegler-Nichols method tuning method. And the for the method. I also have set the KC, the 1 over TAUI and TAUD to get the scope. From this table, we can see here that determination of other parameters for the Cohen-Kuhn for PID controller is KC is 2.9656, tau I is 0.739 KKKK371365 and tau d is 0.1245. After all the parameter has been determined, we can determine the shape of the graph of PID, and this is the frequency response for Cohen-Kuhn for PID after tuning. The Cohen is the graph, and now, based on the simulated for tune result, both PID controller produce different output in Ziegler-Nichols and Cohen-Kuhn. For Ziegler-Nichols, tune result produce decrease of error compared to untuned result. However, for Cohen-Kuhn, tune result produce increase of error compared to untuned result. This might lead to conclusion that Cohen-Kuhn might be suitable for tuning compared to Ziegler-Nichols. This is the last question. The last question is optional for extra 10 marks. Propose any advanced process control strategy and design it in the system. Test the performance of the advanced control strategy and compare with your best controller after tuning from question sheet. My suggestion is the cascade control for advanced process strategy in Cstr, since it involves the use of two controllers with the output of the first controlling provide set point for the second controller, and the feedback loop for one controller nicely inside the other. It can also be explained in other way, where cascade controller means to connect the output signal of one controller to the set point of another controller, which each controller sensing a different aspect of the same process. Here is the control strategy of the Cstr. Temperature of set point is 25 degrees Celsius with flow rate of coolant as the manipulated variable, and the temperature is a control variable. I compare the advantage and disadvantage of the cascade control, which is the advantage are control primary variables more effectively, while the disadvantages are make system more complex. And second, it reduces the effect of dead time and fast lag time in system, while the disadvantages is cascade control require more instrument and equipment, thus increase the cost. The difference between modes are there are two modes which are normal mode and automatic mode. For normal mode, controller takes no automatic action. Output value set by human operator, while for automatic mode, controller automatically adjusts its output to try to keep PV equal to SP. Set point value set locally by human operator. And for the final result is Table 11 saw the comparison between cascade control and feedback control. The feedback control is predictive control cannot occur and control can be unsatisfactory for process with large dead times or are slow. While for cascade control, predictive control will occur and respond quickly to change that occur in system. Second loop have influence in primary loop, so any deviation in process can be fixed quickly. So here is all my presentation for my dynamic and process control computer simulation assignment. Thank you.